Hello everyone and welcome to IInventive 2025. We are thrilled to showcase our cutting-edge R&D work at this prestigious fair, and we invite you to collaborate with us. Our presentation today highlights a pioneering achievement from the VLSI Laboratory, Department of Electronics and Communication Engineering, NIT Silchar, titled Design and Development of Variable Neural Signal Acquisition Front-End Amplifier IC for Brain Vision Interface, led by our esteemed Chief Investigator, Professor K.L. Vaishnav, and Co-Chief Investigator, Dr. Kaushik Ro. We look forward to sharing our innovative work with you and exploring potential collaborations. So, what is BMI system and why we require a BMI system? BMI system is basically an interface between the brain and a computer so that we can extract the behavior of neurons to the computer and further analyzes it. So these are the neurological disorders that are occurring in day by day, and these are some statistics I have jotted down here for your references. We can see here all the neurological disorders exponentially increasing day by day. So we require a robust BMI interface so that we can detect or diagnose this type of diseases, and we can give some preventive measures to the patient. So before designing any BMI system or neural signal acquisition system, we should know what is neural signals and what are the characteristics of neural signals. So these are the slides where I have shown what is neural signals and what are the types of neural signals, amplitude and frequency ranges I have depicted. Neural signals, the generation of neural signals basically occurs due to the interaction of sodium and potassium ions within the brain. So these are the neural signals basically divided into two frequency range: action potential range, that's 100 Hz to 10 kHz, and local field potential, so 1 mHz to 100 Hz. So based on these characteristics, we will move forward to design the acquisition system or BMI system. So this is the typical neural recording system, where you can see the signal is fed to the LNA from a microelectrode array, and the LNA will eliminate the noise and amplify the signal to a certain level. After that, it is fed to the PGA, programmable gain amplifier. If the gain of the LNA is not sufficient, PGA block is used to boost the gain for further processing, and after that ADC is used to convert it in the digital form, and further backend processing is done. So our research work, this work concentrates on LNA design, which is the most important block in this design, which will capture the first incoming signal from the electrode, and in spite of so much noise in it, it will amplify the signal and give it to the PGA for further processing. Now design challenges. Every design has some design challenges. So this is also not free from it. There are some certain design challenges we will encounter during our designing of circuits and other systems. So these are the neural recording amplifier and its design challenges. You can see here. It requires high gain and low power, low area to avoid the excessive hits and thus damage to tissues, for avoiding the damages occurred by the heat. Next, it should be interference free, which required high CMRR, common mode rejection ratio. Also, it requires low noise, as it is very noisy signals. So the amplifier itself should not impose some noises in the signal. Also, it should be a low offset to improve the mismatch, which involves the trade-off with it. As we decrease the offset, we have to increase the width and aspect ratio of the MOSFETs to reduce the mismatches and reduce the offset. So there is a trade-off between the area. Now let's check the topology selection for optimal performance. We have used low noise closed loop capacitive feedback topology, which is optimized for minimal noise, and the midband gain is controlled by the capacitance, input capacitance and feedback capacitance ratio, which is shown here, along with OTM. Another is for low power perspective, that is open loop design. where the midband gain is controlled by the OTA itself. Other topology exist: CAFN topology, which consume high area, Miller integrated feedback network MIFN, and Miller compensated capacity feedback network MCCFN exist. All these topologies have some disadvantages. One has high offset, that is MIFN, and MCCFN consumes high area. So considering all this scenario, we have selected capacity feedback topology for our design along with open loop design. And these are the design criteria and specification taken for consideration for designing the circuit. So let's go to the design. So these are the proposed circuit which is modified from the conventional folded cascode OTA, where we have used one extra transistor for introducing self-bias high swing current mirror cascode current mirror, which ensures high gain and high output swing, and current scaling pulley resistors for ensuring low noise. And these are the modeling analysis of this OTA. We have obtained the gain, small signal gain this much, and input noise, random offset voltage. Based on this expression, we have tuned the circuit for our required design spec, for meeting the required design spec. Let's come to the results. After designing and doing the backend design, we have performed post layout simulation. So these are the comparison between post and pre layout of gain, noise, and the comparison between other state of art work, where closed loop topology reports highest gain, open loop amplifier design reports least power in comparison to the other existing state of art design. These are the pre-layout and post-layout deviation results shown here, where you can see low deviations are obtained in both pre and post layout results. This is the CMRR result, pre-layout and post-layout. And these are the Monte Carlo analysis, where we have varied all the corners of both the proposed work, one for open loop and for closed loop, and all the using all the corner we have simulated, and results are obtained for gain and noise. And this is the final outcome, the tape out of neural amplifier, where we have consumed 2 mm plus 2 mm die size, which is the minimum die size of SCL, and which is designed using 1 poly 4 metal process in SCL 180 nanometer technology. And this is a test setup in VLSI Lab and NIT Silchar, where it is found to be working as an amplifier for low amplitude signals. And these are the overall summary of the work. A neural amplifier IC tape out with high gain and bandwidth has been designed considering noise power trade-off. For improving noise performance, current scaling is done. To improve output swing limitations, conventional cascode current mirror load in the gain stage OTA, a high swing self-biased cascode current mirror load has been used. And the IC tape out consists of two designs. I have already told: closed loop and open loop design. Simulation results and comparative analysis indicate that the proposed open loop neural amplifier reports the lowest power among the state of art design. On the other hand, closed loop capacitive feedback neural amplifier reports a very high gain and bandwidth and a comparably low noise as compared to the state of art design. Monte Carlo analysis further reveals a close agreement to every process corners and temperature with a very low standard deviation, which also proves the consistency in the performance of the proposed neural amplifier. As we conclude our project, we'd like to take a moment to acknowledge the invaluable support we received from various sources during its execution. We'd like to express our sincere gratitude to MeitY for providing EDA tools and fabrication facility at SCL Mohali, NIT Silchar Authority and Department of Electronics and Communication Engineering for providing lab infrastructure support throughout our project. Your contributions have been instrumental in shaping our project into its current form. We appreciate your support and guidance. And this our team, Dr. Koshikyo, Co-CI, Professor K.L. Vaishnav, Chief Investigator of this project, and myself, Dr. Saurabh Nath, Project Associate of this project. Now I like to invite collaborators. If you like to collaborate with us, please contact in this email ID or phone number. You can directly contact. And for more details of this project, please scan this QR code. And these are the references we have used. Thank you.